That was 1990, 1989, 88, something like that. And what he did is he raised a bunch of money and embarked on this. He started a business and started doing basic research into basically proving that hydrino atoms exist and can be used to generate electricity. And so this has been a 25-year quest for him and his team, everybody working with him. And we're going to kind of walk through some of the interesting stages of this journey. What you see here is an electrochemical cell, which is composed of, in order to get this reaction to happen, you have to generate hydrogen. In order to do that, a good way to do that is to electrolyze it from water by splitting water into hydrogen and oxygen. And you can do that in an electrolytic cell because it has an anode and a cathode, and it'll split water. But in order for this reaction to work, you also have to have a catalyst, like the lithium atom I mentioned before. In this case, it's potassium, which comes from potassium carbonate in the electrolyte. So in this device, what you have is you have hydrogen and oxygen splitting in the cell. You have the hydrogen interacting with potassium in the electrolyte. The potassium is able to ionize electrons during the reaction, allowing hydrino atoms to form. The hydrino then just kind of diffuses out of the cell, and the only evidence that you see that was ever there is that you're getting excess heat from the reaction. Mills was able to get way more energy out of these cells than cold fusion scientists were, because he was actually using the right catalysts and he was optimizing the conditions for the reaction to occur. And he was able to consistently get a lot of excess energy, often hundreds of times more than could be explained through conventional chemical reactions occurring in the cell. One reason why this may have been ignored by most scientists is that it is very similar to the cold fusion cell, and there was a lot of cold fusion experiments happening at the time that a lot of people were deeply skeptical about. So they started experimenting with essentially hydrogen plasmas. Now, a plasma is a state of matter in which you have charged species that are incredibly hot, like the sun, like the material of the sun. It's a plasma state. And so what you really have to do is you have to heat up the cell. You have to have a gas in the cell. You have to heat it up, put some current through it, and it'll form a plasma. And when there's a chemical process happening that can speed it along, then the plasma will form in ways that you don't expect it to. So, for instance, with these experiments, which they conducted over the course of about 10 years and resulted in about 60 or more scientific publications, they were discovering all of this interesting phenomena in their plasma cells that got a lot of scientists scratching their heads. So they were discovering light emissions and frequencies that they were not expecting, or that scientists would not typically expect. They were able to form plasmas at very low initiation voltages. They were seeing very interesting, they were seeing really wide line broadening, which was indicating there were very hot populations of gases in the cell. And all these questions, all these phenomena raise the question, well, there must be some kind of chemical process in the cell that's producing this plasma. And when you turned it off, there was this extremely long afterglow duration. And these were studied by experts in plasma physics, and some of the most important backers of Mills's experimental work were, like Joseph Conrad's. He was one of the world's most respected plasma physicists, and he ended up publishing on this topic too. This is a pinch discharge plasma cell, and the goal of this was to, you can inject an enormous amount of current into a small sample, and you can get the hydrogen will actually form hydrino under these conditions, and it'll emit radiation in the extreme ultraviolet wavelengths. It'll emit continuum radiation, a large band of continuum radiation. And I should point out that it's impossible in conventional chemistry to get an extreme ultraviolet radiation out of pure hydrogen. But they were able to do it. But this is kind of to show that, science is like It's like the braided streams. It's a metaphor I use in the book. It's, they took a lot of twists and turns. They experimented with a lot of different reactor cells. I worked there for a number of years, or actually I worked there 18 months on site, and then later did other kinds of work with Mills in the years afterward. But you know, science is slow, and you have to explore a lot of different possibilities, and they were building a lot of different kinds of reactor cells, plasma cells, electrolytic cells, closed cells, open cells. Some of it was basic research whose only goal was to really show either chemically characterized hydrino atoms and molecules, or to just prove that that heat was being released by the reaction. But all this time, they're also thinking, well, we'd really like to commercialize this and you know, turn it into a viable power source. The real breakthrough in their science came a few years ago when they kind of rediscovered the value of water molecules as a potential catalyst. So a water molecule, if it's not closely bound or attached to other water molecules through electrostatic forces, if it's free, it can actually allow, it has two things in it. It has hydrogen source and it has a catalyst, because breaking the hydrogen off of the oxygen, you can actually create a hydrino, and you ionize the oxygen, and then breaking the molecular bonds and the ionizing electrons will provide the magic number, the 27.2 electron volts you need to form a hydrino atom. So it all comes in one package in a water molecule, which is interesting. And so what they developed was they developed this little capsule that contained 70 milligrams of water and 30 milligrams of like a titanium oxide powder, a conductive powder. And you'd wrap it in foil, you'd put it on, you know, put it in a spot welder essentially, and shoot a burst of current through it, a burst of very high current through it. And this capsule would vaporize instantaneously. It's actually an explosive reaction that consumes only water. The metal powder can actually be recycled. It can be captured and recycled. The only thing consumed is the hydrogen. And so this was a watershed moment for them, because finally they have a reaction. They have a way to get the reaction to happen at an extremely high power density, way, way, way higher than anything they'd achieved to date. And when you have an explosive reaction, well, you suddenly have something that's feasible as a power source. You need to be able to control it, you know, but it was a huge breakthrough moment for them. So the quest for the last several years has been, well, how do we turn this into a viable, continuous power source? And so I'm going to start talking about a series of prototype reactor cells that have been developed by Mills and his team at what is now called Brilliant Light Power over in Cranbury, New Jersey. And I'm going to start, I figured out to read a little bit for you from the book. So I'm going to read a small piece here, a small passage that talks a little bit about this. When Harlan Bretz hiked across the scablands, he found braided streams etched across the landscape. Perhaps all of science is scouting the braided streams. The paths meander here and there. BLP followed a path that began in electrochemistry, passed through a decade of plasma physics, then new catalysts, then back to electrochemistry, and a constant interplay of theory and experiment, each informing the other. However, it was clear that in the wider scientific community, observation was no longer the arbiter of truth. Hydrino research would be ignored so long as it only manifested as low-grade heat, or light-emitting plasma, or unusual materials, or high gains from tiny cells. Mills needed power that could not be denied, a reaction rate that went beyond anything he had achieved to date. When the streams converged and Mills realized what was limiting hydrinocatalysis all these years, the result was explosive. In a breakthrough experiment on November 14th, 2015, which was not that long ago, they had injected water vapor into molten silver and poured it between tungsten electrodes, hitting it with rapid bursts of current. The intensity of the hydrinocatalysis vaporized the silver as it passed through. They found they could create and sustain a brilliant glow. In the prototype reactor, now on the bench as of the completion of this book, the alloy is heated to melting point and pushed up with an electromagnetic pump into a basin between the electrodes. That's what you're seeing here. The molten silver is being pushed up with an electromagnetic pump up between these electrodes, and current can then be injected when the silver passes through. When the silver reaches the electrodes, it triggers the current flow, injecting a rapid succession of high current sparks from a bank of supercapacitors. At first, the green sparks emit primarily in the extreme ultraviolet and soft X-ray wavelengths. There's not much for the human eye to see. Then you see a beautiful golden light emerge, flickering with molten metal spilling out like a volcano boiling over. It is fragile, struggling, almost masked by the smoke of vaporized metal that plumes from beneath. Beyond the smoky plume is a light that grows, steadily but surely, penetrating through until it enraptures you in its golden light, like watching a glowing campfire in the middle of the night. And though you don't expect it, it grows still, washing over you in waves, and when you feel it could not be more beautiful, the gold, now solid and unwavering, grows to white, and the white begins to beam. It overwhelms everything in your peripheral vision, and you find yourself staring into an impossible brilliance. The night no longer exists, for the campfire has become the sun. It is a sun that we can make at will. It is capable of growing food through an Arctic winter and carrying water to a parched land. A sun that may be used to power every facet of our civilization in ways we have not yet imagined. So in this prototype, what's happening is the reaction is happening here. It's producing this brilliant light-emitting plasma. The light is primarily in wavelengths that the human eye cannot see, but can be captured with spectrometers. The idea here is that there's a tungsten shield over this basin, which is actually getting hot, getting heated up, and re-emitting light within the visible wavelengths. And the reason for that is because you could then surround this device with solar panels, high-density collector solar cells, and you can capture that light as solar power. So it literally is a sun in a box. And this was the prototype that was on the bench maybe 6 or 8 months ago. So one problem they kept having with these devices is that the hydrino-catalysis reaction was producing so much heat that it was vaporizing the electrodes. Now the electrodes are being built out of tungsten, like 99.9% tungsten, which it's very hard to vaporize. It's very hard to melt, very hard to vaporize. It requires an extremely high temperature, and they were vaporizing these electrodes in seconds, in 10, 15 seconds. So that gives you some sense of the power of this reaction and how much energy is coming off of it. It is hundreds of times more powerful than combustion. The reaction of hydrogen and oxygen is a rocket fuel. It's a good rocket fuel because it uses a lot of hydrogen, which is a light element. But it's an extremely energetic reaction. We're talking about hundreds of times more energy density than that reaction. So Mills had this great idea, which was to get rid of the electrodes and use 2 independent streams of molten silver as the electrodes. So what happens is they get pushed up by electromagnetic pump into this globe, into the reaction cell. And when they meet, the current arcs across them. And so you are basically using liquid electrodes. And the reaction's happening there, and you're injecting pure hydrogen into the cell. And the oxygen, you have an oxide that also gets added to the cell, which stays in the cell. The fresh hydrogen is actually permeating in through that sphere, and the hydrino is actually permeating out. But the oxygen stays in the cell. The oxygen forms water, allows the catalysis reaction to occur, and then it remains in the cell and gets recycled. So the only thing that's consumed in this process is hydrogen. And this is the latest prototype that they have on the bench right now. I was just there yesterday and got to see this for the first time. Here's their demonstration model. It looks really big and complicated, but really this thing can sit on this podium. It's only like this high. That sphere is only this big. It's an incredibly awesome amount of power that's being generated in an incredibly small space. One of these units, when it's integrated with PV, they're going to release an alpha unit which starts at 30 kilowatts, which is enough to power a few homes. They're going to steadily improve the device by adding a more sophisticated solar array that allows them to capture a wider frequency, or a wider spectrum of light from the cell that will allow them to go up to 60 kilowatts and eventually up to 250 kilowatts. So one of these units should be potentially a 250 kilowatt power generator that consumes only water. It's almost unbelievable. This is what's happening in some of their earlier prototypes, is they were vaporizing these extremely high melting point metals in seconds, and I'm going to show you one.
Turn it down a little bit. Oh shit, I can't see. All right, come on. Maria says what's wrong with you? Oh my god. Oh, that's so bright. Oh, turn it down, Brian. All right, ready, 200 amps. Turn it off.
I've never listened that closely to the audio.
I can't even see anything.
Okay, so that was, I think, a molybdenum electrode that just vaporized. All right?
Yes, everything on. Yes, everything on.
And that's what produced this. So this is, like I'm saying, it's the highest controlled power density reaction known to man. And this is happening not too far from here.